Okay, well done if you've got this far. This is the last example on the Applied Mechanics course. And well, just congratulations, and hopefully this course has been helpful and you've managed to understand what we've been through. Anyway, usual approach here. Read the question carefully, lift out the key information. Velocity, t seconds, given as a function of t. So function of t, therefore not constant acceleration. We're in an integration differentiation kind of context. When t equals 0, the vector of p with respect to a position is 2i minus 4j, so we're given a position vector at the start. Find the position vector of p after t seconds. Okay, so part A. We've got the velocity, so let's integrate then. So v is equal to 3t squared minus 8, lots of I, plus 5j. The integral of v dt to get to the position is equal to, write down the constant, add 1 to the power, divide by the new power. Write down the constant, and minus 8 becomes minus 8t when we integrate, and we need a constant of integration. Call it c1 lots of I, plus integrate the plus 5, so we get 5t, plus our constant of integration, c2 lots of j. Don't forget the bracket, so we clearly define the vector I and the vector j. Yeah, the brackets are really quite important. Okay, so we can now put in our boundary conditions which come back from the question. In the question we were told at t equals 0, r was equal to 2i minus 4j. So if we lift out and think about the components separately, so coefficients of I are going to give us t cubed, simplifying the 3t cubed over 3, minus 8t plus c1 is equal to 8, hang on, what? No, 2 minus 4. So that's 2, and that was when t equals 0. So actually I should have written 0 cubed minus 8 lots of 0 plus c1 is equal to 2. So c1 equals 2. Look at the j components, and we get 5 lots of 0, substituting t equals 0 in, plus c2 is equal to the minus 4. Let's just highlight those up so it's clear where they've come from. So the I components come from here to give that line, and the j components come from here to give that line. Tidy that up then at the end here. C2 equals minus 4. So we can substitute back in, and we've got r is equal to t cubed minus 8t minus 4. Sorry, that's plus 2. Looked up at the wrong one. Plus 2, lots of I, and then plus 5t minus 4, lots of j. Okay, find the position vector of p after t seconds. And actually, as it's written here in a bold way, whoops, Yeah, this one, that p was bold. We probably should write down here, make it clear that this is the vector p. So p is equal to t cubed minus 8t plus 2I plus 5t minus 4 lots of j. Okay, part B. A second particle q moves with constant velocity 8I plus 4j. When t equals 0, the position vector of q with respect to an origin O is 2I. Prove that p and q collide. Okay, so what we need to know is the position of p, or the position of q at time t. So B, Q, that's the position of Q, is going to be equal to, and in general terms this is fairly useful as a way of thinking. So let's just give a general equation. R, the position of something, is equal to where it starts plus how far it has moved. Yeah? So R0 is its starting position. Starting position. And this is how far it's moved. How far moved. But given something in particular, what have we had for that equation to be true? There's something else that's got to be true. Right? True when acceleration is constant. So here for Q, let's just check the question. I think a second particle Q moves with constant velocity, yes. So it's got constant velocity of 8I plus 4j. And its position vector is 2I at t equals 0. So if we come down here, we've got Q naught plus the velocity of Q times the time. Okay, so Q naught, its starting position from the question was 2I. So that's 2I plus how far it's moved, which is 8I plus 4j. So 8I plus 4j lots of t. We usually collect the vectors together, so the I components together, so we're going to get 2 plus 8t lots of I from here. That's an I component, that's an I component, t to give us that, plus 4t lots of j. So that's got the position of Q at time as a function of t. Now let's read the question. Prove that P and Q collide. So for them to collide, yeah, they must have the same position at the same time. To collide, same position at same time. Okay, so let's consider the I components. In fact, it's probably easier to consider the j components. Yeah, the functions are simpler, aren't they? Yeah, so consider the j components. We get 5t minus 4 is equal to 4t. Yeah, the j component and the j component of their positions must be equal. Well, that's fairly straightforward to solve. That gives t equal to 4 seconds. Now we consider the I component. Consider I, so of p first of all. So we get 4 cubed minus 8 lots of 4 plus 2. Substituting the 4 into this equation at the top of the page here. There's the I component that we've substituted in for t, and t was equal to 4 down there. So we get 64 minus 32 plus 2 equals 34. Now if we think about of Q, we get, where's the equation? For Q is there, the j component, sorry, the I component is 2 plus 8t. Yeah, that's this bit here. 2 plus 8t. So 2 plus 8 lots of t, which is 4, equals 34. Since I and j components same at t equal 4, p and q will collide. And that is it, the end of the course. You obviously now need to do a little bit of practice on those style of questions. So can you have a look at exercise 8E? Questions 2, 4, 6 and 8. That would be great, and good luck with those.